In section 3.7, we're going to be working with optimization problems that optimize some quantity. And you'll notice in this first problem, and by the way, you can get a printout of these 4 problems from Blackboard. But in this problem, we're going to optimize the area. So I'm going to start by jotting some basic information down, a rectangle sketch with its length and width. I'm going to use an X for width. And then I'm going to define each of the variables. That's an important step of any application problem. And next, because I'm given the perimeter, I'm going to write the perimeter to formula 2 times the length plus 2 times width equals 100. So I'm able to use that to get that the length is going to be 50 minus x. And now I am all set to write this quantity that I'm trying to optimize as a function of x, because the area with respect to x is going to be x times 50 minus x. That's the first legwork for this problem. The next step is to find the derivative of the area, because if you recall, the maximum or minimum area will happen either at an end point or at a critical number. A critical number is a value for x that either makes the first derivative 0 or undefined. And let's talk about endpoints, because if we have 100 feet of fencing, notice that our x is going to be somewhere between 0 and 50. Because, for example, if we had a zero width, then we'd have a length of 50. This doesn't really 0, but if you could picture these side by side so that this quantity was 0, we'd use up 50 units, or in this case, 50 feet of fencing. And obviously, that's where we're going to get area that's minimized, because the area of 0 times 50 would be 0. But we do want to always note the domain of our x. So let's go about the first derivative. First, I'm going to distribute that x so that I get it's easier to work with. And the first derivative will be 50 minus 2x. When I set that derivative to 0, I get x equals 25. So now I've found the critical number. The last step is to evaluate the area at each of the endpoints and at the critical number. And notice that I'm to evaluate the function at each of the critical numbers and at the endpoints. I'm going back to the equation, the original function. You could use either forms of that function, but we need to use that original function, not the derivative. We can finalize this problem by saying, therefore, the max of 625 feet squared is achieved when width is 25 feet. And that wraps up problem number 1. Let's look at the second problem, example 2, an open top box. An open box is made from a 16-inch by 30-inch piece of cardboard by cutting squares of equal size. So notice that if I called this red distance x, then notice what's left here. If it was 30 inches all the way across, then this yellow segment will be 30 minus x. This green segment was 16 inches all the way across. So, and I'm sorry, I left the 2 off, would be 16 minus 2x. So we've got this yellow length is 30 minus 2x. This green length is 16 minus 2x. The entire distance, the length, was 30. If I subtract off both of these x's, I'd be left with 30 minus 2x. And now, what is it that we're trying to maximize? We want to maximize the volume. So I'm going to need to write a function that defines the volume. So the variables we'll need to define, let V equal the volume, X is the square's side. Now I can write a formula for volume, length times width times height. As the length is going to be 30 minus 2x, the width is going to be 16 minus 2x, and the height, when I fold those sides up, will be x units tall. Probably a better way to state this is to write it as V of x. The volume with respect to x, where x is the length of that side. I can multiply this out to simplify it so that I can next find the first derivative. Let's remember to state what our constraints are. What's the biggest and smallest x possible? Well, the smallest x would be if it doesn't exist at all. If we didn't cut anything, then of course the volume's going to be 0 because we'd just be looking at a flat piece of paper. The largest x is if we went halfway across the smallest side. Because if we went halfway across the large side, 15, and we couldn't get a square that was size 15 because this width, the 16 over here, wouldn't have enough width to cut 2 15s from it. So our x, our square, can go anywhere from 0 to 8. I'm going to jump ahead slightly and show you what this would look like. I'll leave the algebra to you. But when we do the derivative, we'd have 480 minus 184 plus 12x squared. And if we set to 0, we can find our critical numbers. I'm going to leave the algebra to you there, but let me give you a tip and say that the greatest common factor is 4. So if we start factoring out that 4, this piece will be easier to work with. You could now solve this quadratic equation by factoring or by using the quadratic formula. We get these two values. Notice that our 12 is too big. It's outside our constraint of 8. We can only go up to 8. So I'm going to throw this one out. And the only usable x is going to be the 10/3. So the last step is to find what the volume is for when x is 0. We've already decided that was going to be 0. X was 8, we'd have a 0 volume. The volume, when x is 10/3, we could go back to our original equation here, replace that x with 10/3, and we'll get 19,600 over 27, or approximately 726 inches cubed. So to write the final answer, we'd say therefore max volume of 19,600 over 27 inches cubed is achieved when the square's side is 10/3 inches. That's problem number 2. Jump quickly into number 3. The third example, an offshore oil well. We have an offshore oil well at W, and we've got this shoreline over here. Now, if the is 5 miles from the coast, then we're going to write that as a perpendicular length. And then we've got some point B here, and this distance is 8 miles. And what we're going to do is, our goal is to get the oil from point W to point B. The reason we don't want to go straight across is because it's more expensive to have underwater pipes. The better optimization way to do this problem is to plop down a point here somewhere between A and B, and to take the water or the oil from W to P, and then from P to B. Notice the costs associated here. From P to B is going to be $75,000, and from W to P is $100,000. So the last thing we need to do is set up the variable. Let's let x equal the distance A to P, and now we could call this PB 8 minus x, and we could also say that it's going to have to fall between 0 and 8. The last piece of information we could draw from this is we could use a Pythagorean theorem and say that this distance from W to P, we knew this 5. So we know that the distance from W to P is going to be the square root of 5 squared x squared. So it's the different information we have to work with. Let's go ahead and write this as a cost. The cost with respect to x is going to be the blue part 1, or let's use a 10, or 100. Let's use a 100 and drop the zeros on both of these amounts. So the cost is $100,000 times the blue length, the 25 plus x squared, added to $75,000 times the yellow length, and there's our equation. Our next step is going to be to find of this. I'm going to leave to you and the list of calculating this. The question on how to do the derivative Please question to class. But we'd get, this is the derivative, and I could simplify it by removing a 5, by factoring out a 25. What happens when we set this to 0? I'm going to use this form of the equation to set to 0, because now all I have to use is that piece in the parentheses. And here's where we'll have to apply some algebra. I'm going to solve this radically by isolating the side of the equation by writing a proportion, so that this 4x over the square root is on one side and the 3 is on the other side. And then I can use cross multiplication. 1 times 4x equals 3 times square root of x squared plus 25. Divide both sides by 3. And then square both sides. When you work that out, we'd get 15 over the square root of 7, or negative 15 over the square root of 7. And we know it can't be negative, so the answer is x equals 15 over the square root of 7. We could now go back to our original function, c of x. Let me pull it up on the screen. And find c of 0, c of 8, and c of 15 over the square root of 7. The cost when x equals 0 comes to 1,100. The cost when x equals 15 over the square root of 7 comes to 600 plus 125 square root of 7, or approximately 930.719. And the cost when x equals 8 comes to 100 square root of 89, or approximately 943.398. So it looks like our minimal cost is when x is equal to 15 over the square root of 7.